So as we completed that last exercise, many of us may have seen something interesting, especially on the last two questions. We may have found that we came up with different answers, and in some cases many different answers, that all fit the same chemical formulas. And as I mentioned in that video, it didn't mean that some of us were right and some of us were wrong. There certainly are wrong answers, but there are cases, and in fact many cases, where we can have multiple multiple structures that fit the same chemical formula. And so this idea is known as isomers. Isomers are compounds with the same chemical formula but different structures. Now, how important is this? Well, here's an interesting example. So for the molecule with chemical formula C8H18, there's a number of different compounds that we can draw with this chemical formula. And let's look at a couple of these. So this first one is just a straight chain of carbons, C8H18. And the name of this molecule is octane. Now, octane is something that we might be familiar with. Where have we heard of octane before? We often hear that term when we buy gas for our car. Anyone know the octane rating of pure octane? Equal to -20. So even though we use this term octane rating, it turns out that octane itself is something you'd never want to put in your car. But what if we rearrange our carbons a little bit? So here's our carbon skeleton, and you can see we still have 8 carbons here. It's just we've rearranged how they are. And we'll also fill in the hydrogens. Although you'll see in a little while, that's something we're going to stop doing. This compound is known as Iso-Octane. Once we learn some nomenclature, which will come up in a couple chapters, we will also learn that this compound can be known as 2,2,4-trimethyl pentane. But regardless, what's the octane rating of iso-octane? Iso-octane has an octane rating of 100. So just simply by rearranging how those carbon atoms are within the molecule, it can lead to some pretty significant consequences. And as we go on in this course, we'll see many other examples where similar types of things can happen. So how many isomers are possible for different molecules? Well, the answer is it depends on the chemical formula. And the more carbons, the more hydrogens we have within a molecule, the more isomers we can have. So for example, with the simplest possible molecules, CH4, C2H6, and C3H8, there is only one possible way to arrange them. But as soon as we hit 4 carbons, we can have 2 different isomers. And as our number of carbons go up, so does our number of isomers. So at 7 carbons, we have 9 possible isomers. And at 8 carbons, which we were just working with for octane, we saw octane, we saw iso-octane, but there's actually 16 more. So what if we go up to 10 carbons? How many isomers do you get then? 75. What about 20 carbons? Then we get to 366,000 possible compounds. So one of the important points becomes here is that chemical formula is no longer good enough to describe what the compound is. Once we get above a couple of carbons, we need to have structures or names. And this only gets worse. What if we have 40 carbons? At that point, there's more than 62 trillion possible isomers. And we'll end at C100. So if you have 100 carbons, there's more than 10 to the 39th possible isomers. Now, how was this determined? Obviously, you couldn't draw all these out. So it turns out that someone went through and figured out how to calculate all of these. And I'll paste the link in here if you're interested. The only problem with this publication is it is unfortunately completely in German, and so I'm not really able to tell you much more about it. But let's get back to compounds. So as we said previously, and as we were going over the first in-class exercise, there's a lot of generalizations that can be made with bonding. And so in general chemistry, you probably learned a series of rules for drawing Lewis structures. Sum up your valence electrons, draw bonds to your central atom, add in your lone pairs, and then add in double or triple bonds as necessary. And while in theory you could still do it that way in organic chemistry, as we progress into organic chemistry, that becomes not very feasible. And the reason for that is that in organic chemistry, the molecules are just going to be too big. And as you started to sum valence electrons, you'd literally be getting 70, 80, 90, 100 valence electrons. And so what we end up needing to learn are some of these general rules. So I will never make you memorize any part of the periodic table. But that being said, there's certain parts of the periodic table that if you know by memory, it's going to help you a lot. And to be perfectly honest with you, even if you don't try to memorize these parts of the periodic table, you're going to find that it happens anyway. And so with these elements, our most important ones, carbon, nitrogen, oxygen, halogens, and hydrogen. First question, how many valence electrons do they have? Carbon has 4, nitrogen 5, oxygen 6, the halogens all have 7, and hydrogen, of course, has 1 valence electron. So what then do each of these elements need? Well, if carbon has 4 electrons, it needs 4 more. So carbon will form 4 bonds. And can we say that carbon always forms 4 bonds? Yes, that is something we can definitely say. Carbon always forms 4 bonds. Nitrogen has 5 valence electrons, and therefore needs 3 more. So in its normal state, nitrogen will form 3 bonds and have 1 lone pair. Oxygen has 6 valence electrons, which means it needs to form 2 bonds, and then has 2 lone pairs. Each of the halogens have 7 valence electrons, and so they form 1 bond and have 3 lone pairs. And finally, hydrogen being in the first row, remember an octet for hydrogen is 2 electrons. So it has 1, it needs 1 more, it will form 1 bond. So these are some general rules that if we keep in mind can help us out and help make drawing Lewis structures a lot easier. Now, one of the reasons we need to do that is because if we have to draw out every atom in every molecule, you saw on the practice sheet that we did that even something as simple as C10H22, which is a fairly simple organic molecule, that took us a lot of time to draw out that molecule. So how do we solve that problem? So again, here's our Lewis structure. And we're going to do this for propane. Well, the first thing we can do is we can draw what's known as a condensed structure. By a condensed structure, what we're going to do is we're going to take each carbon and whatever is on that carbon and group it together. So that first carbon that I've highlighted in green, we can see has 3 hydrogens. So we'll group those together, CH3. The next carbon, which I've highlighted in purple, has 2 hydrogens on it. So we'll put CH2. And the last carbon, which I've highlighted in this blue color, has 3 hydrogens, so we can abbreviate that as CH3 as well. And so our condensed structure still shows us all of the same information that the Lewis structure did, but it makes it more compact and allows us to simplify things. But we can go even further, and typically we do. And what that means is the most common way for drawing structures are what we call line structures. A line structure for propane looks like this. Now, where did all the atoms go? So the first thing we want to find are the carbons. Anywhere that 2 lines come together, such as this point I've highlighted in yellow, is a carbon. Anywhere that a line ends, such as over here or over here, is also a carbon. So there's our 3 carbons. What about the hydrogens? Well, because we know carbon always has 4 bonds, we assume that there are enough hydrogens to form 4 bonds. So we're going to redraw this structure on the next page. So we've already established that there's a carbon here, carbon here, carbon here. So again, what about the hydrogens? Well, let's look at this first carbon. How many bonds do we see for this carbon? So we can see it's bonded to 1 carbon. That's what the straight line is coming out of it. So how many hydrogens does it have? Well, if we have 4 total bonds, then it must have 3 hydrogens. Same thing is true on this side. But the one in the middle, this carbon, we can see it's bonded to 2 carbons. Therefore, it has 2 hydrogens that are not drawn in. So why do we do this? Why do we leave all these atoms out? Well, the reason we do this is it keeps our drawings simple. You know, if you go back to the molecule we started with, Taxol, so do you recall how big Taxol was? If you don't, let's put its structure back up. So there's Taxol again. We're going to ignore diacetylbactam. What's the formula here? C47, H51, NO14. Just imagine how cluttered this drawing would look if we had to draw in every one of those 47 carbons and every one of those 51 hydrogens. It would just become messy, and it would be a lot harder to understand what was going on with the structure. Now, most molecules we look at are not going to be this complicated, but we can still see it helps us to simplify and helps us to focus on what's important. What about other atoms? For example, nitrogen or oxygen or halogens. Those are actually pretty easy. Why? Just draw them in, like you normally would. And this includes H's that are on non-carbons. So the hydrogens that are on carbons, you can leave out. They don't have to be shown in a line structure. Any other hydrogens do. What do I mean by that? Well, let's look at ethanol. Ethanol has this chemical formula. If I want to draw it as a line structure, I draw it like this. I cannot draw it like that though, because now there's only one bond on that oxygen. We never assume hydrogens on non-carbons. So we know that this carbon here, the first one, we see one bond, we know it has 3 hydrogens. Our second carbon, we can see it has 2 bonds, one to the carbon, one to the OH group. So we know it has to have 2 hydrogens. But the oxygen, we don't make any assumptions about, and it's exactly the way that it's drawn in. All right, from here, you should get out in class exercise number 2, which has to do with practice of line structures, and work on those, and then we'll come back and go over them.